This is an AP chemistry exam review that is meant to go over the big ideas, number 4 through number 6. So big idea number 4 is about kinetics, number 5 is thermodynamics, and number 6 is equilibrium, which are all topics that are almost all guaranteed to show up on the AP chemistry exam in May. We're going to use old AP chemistry exam questions from 2013 all the way through 2017 to help us review for the types of problems that will be asked about kinetics, thermodynamics, and equilibrium. So here's our first problem. They give us an equation. N2 plus O2 gives us NO, and then there's two of them. And at high temperatures, N2 and O2 can react to produce nitrogen monoxide, as represented in the equation above. A, write the expression for the equilibrium constant Kp for the forward reaction. So we have to recall that all equilibrium expressions are products over reactants, and we can only have either gases or aqueous solutions. And if they're aqueous solutions, usually it's a concentration, but this one is asking about Kp. So usually it's about a gas. So we'll write Kp, and then its pressures. So this is of the products, and my reactants are N2 and O2. And then the last thing that we need to make sure that we always do is that we include the coefficients. So if there's a 2 there, there has to be a 2 here, and usually you kind of write a parenthesis. So that is my equilibrium expression. B, it says a student injects N2 and O2 into a previously evacuated rigid vessel, meaning that there's nothing else in it and the volume will not change, and it raises the temperature of the vessel to 2,000 degrees Celsius. At this temperature, the initial partial pressures of N2 and O2 are 6.01 atm and 1.61 atm respectively. So they give us some initial partial pressures. When it says respectively, it means that the values are linked in order of my gases. So N2 is 6.01 and O2 is 1.61. The system is allowed to reach equilibrium. The partial pressure of NO at equilibrium is 0.122. Calculate the Kp. All right, this screams to me icebox. So what I want to do, if you're not familiar with an icebox, which is really just easy stoichiometry, is I want to talk about the initial, the change, and the equilibrium. So initially, it says that I have 6.01 atm and 1.61 atm. What is nice is that you can use pressures in an icebox. Pressures, moles, or molarity. I don't have any of my NO, but then it says at equilibrium, I had 1.122. So the change is based on the coefficients. Now, if you're looking for Kp, Kp equals the equilibrium. So if I know I'm finding Kp, it's very important to understand then that you must know all your equilibrium values. All right, so in theory, this is my relationship, but I should be able to figure out what my x is. Right? Based off of this math, if 2x equals 0.122, then my x would be 0.0610. So that means that I must know all my values. So by plugging that in, I'm just going to use my equilibrium expression here. And it's going to be 122. I have to square that over now my adjusted pressures. Where did I get that? Because this is my x. 0.0610 is my x, so 6.01 minus 0.0610 would be 5.95. Right, this would be my 5.95, and this would now be my 1.55. Calculate that out, and then I get a value of 0.00161. And that is my Kp. All right, so we'll shrink A and B there, so it's still there, but now we're going to look at C so we can keep the problem on our screen. It says nitrogen monoxide can undergo further reactions to produce acids such as nitrous acid, HNO2, a weak acid with a Kp and a pKa of certain values. So C, a student is asked to make a buffer solution with a pH of 3.4 by using 0.1 molar HNO2 and 0.1 molar NaOH. I, so they're going to break it down even further. Explain why the addition of the NaOH to the HNO2 can result in the formation of a buffer solution. Include the net ionic equation for the reaction that occurs when the student adds the NaOH to the HNO2. Because it's asking for an equation, the best way to help explain this if you are looking at a problem like this and getting confused is to actually start with the equation first. So the key to this is that you need to understand that my NaOH is a strong base while my HNO2 is a weak acid. Weak acids and weak bases do not break up, but strong acids and strong bases do. So the major component of my strong base is an OH minus. So my equation would actually be acids and bases always react together, but I'm going to do my full acid with only my OH minus. So what do bases do? They take, or they receive H's. They receive H pluses. So that OH minus is going to become H2O. So my HNO2 acids donate. H's become my NO2 minus. So what is a buffer? A buffer is a solution that has, a perfect buffer is solutions that have equal amounts of an acid and its conjugate base. So here I have a pairing of an acid and its conjugate base. And that is really the explanation. The explanation is the fact that it's a buffer is because it has amounts of the acid and its conjugate base. So that is why you could explain why it is turning into a buffer solution, because I have amounts of this pairing. So you could write that out. And that would be 2 points on an AP exam. One, writing the equation. Second one, writing about the fact that you have amounts of each of those partnerships. Double I, determine the volume in milliliters of 0.1 molar NaOH the student should add to 100 mils of the HNO2 to make a buffer solution with a pH of 3.4, and then justify your answer. I believe the key to this problem is the information right here. And it started getting me to think about what is the Ka and the pKa being given to me. So what I did for a moment was I took negative log of my Ka. So negative log of 4.0 times 10 to the negative fourth. And what I got was 3.4. So that is the pH that they're asking about, right? And then you remember, oh my gosh, yes, pKa, when they want a pKa and a pH at the same time, then that has a certain meaning. If you have a pH that equals the pKa of the solution, that's a perfect buffer. And what that means is that your acid equals your base. So what we need is for half of my acid to be converted to my conjugate base. So if I started with 100 mils of my acid, that means I would need 50 milliliters of base to convert half of my acid, which I started with 100, to my conjugate base. And then that would be a perfect buffer. And we know that by the Henderson-Hasselbalch equation, where we have pH equals pKa plus the log of the base over the acid. So the resulting pH will be 3.4 because I'll have equal amounts of acid and base, which make this 1, which makes then this whole relationship right here 0. So then my pH will equal my pKa. All right, we'll shrink that up, and let's look at question letter D. I believe that this one also requires an equation, although you could do this without one. It says a second student makes a buffer by dissolving 0.1 mole of Na2 or NaN NaO2. So that's a salt in 100 mils of the 1 molar nitrous acid, which is more resistant to changes in pH when a strong acid or strong base is added. The buffer made by the second student or the buffer made by the first student in part C. Justify your answer. Okay, so let's take a look at what happened. I have this. This is for part C, where we had this equation. And this is for part D, where it's just the acid. And the reason why I know that is it's adding, you're adding the NaNO2, which that all just goes into that part. So let's label some things here. So I had a certain amount, I had equal amounts of the HNO2 here, and then it drove it to the right, and then you made some more NO2 minus on this side. Whereas it says determine the volume. So basically you had 50 mils of each. We haven't done the moles, but it ended up being 100 mils, and then 50 mils of it from the NaOH drove it to the NO2 minus. In the other one, you're having 0.1 moles of this starting off, right? And then if you have 1 molar of 0.1 moles So more or less what we did was, sorry, if I rewrite this out, I started with 0.1 moles, but then it got converted to 0.05 moles as I made 0.05 moles on this side because there's 50 mils of 0.1 molar. So although I have equal amounts of both, a buffer, a perfect buffer, has equal amounts of a acid and a conjugate base, or a base and conjugate acid, and the larger amount can help resist pH change more. So the answer is the student from letter D, or the second solution, because it has larger amounts. They're both equal amounts, but the larger amounts of the acid and the conjugate base will resist pH change even more. All right, final question. It says a new buffer is made by using HNO2 as one of the ingredients. A particulate representation of a small representative portion of the buffer solution is shown below. Cations and water molecules are not shown. Is the pH of the buffer represented in the diagram greater than, less than, or equal to 3.4? So remember, 3.4 was the pKa, meaning that we had equal amounts of this, the acid, and the conjugate base. Got to remember what that meant. All right, if it's the pKa, that is when those two equal each other. That is when the pKa, the negative log of my Ka, you have equal amounts of your acid and your conjugate base. Justify your answer. Okay, if they give you an image, you simply have to count it. So I have, of the HNO3, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I have 10 of these, and of the NO2 minus, I have 1, 2, 3, 4, 5. So what does that mean? I have more acid than I have base. But they are not equal amounts. So the answer then would be that the solution of the pH would be less than 3.4. Why? It's going to be more acidic. More acidic means that it'll be a lower pH. So because I have a greater amount of my acid, my pH is going to be less than 3.40. So we're going to look at our second problem here. We're going from an equilibrium problem to a thermodynamic problem. So we have an image here. It says a student performs an experiment to determine the enthalpy of combustion. So basically the amount of energy flow that comes from combustion of 2-propanol. The student heats a sample of water by burning some of the propanol. The alcohol burner uses a wick to draw liquid up in the flame. The mass combusted is determined by weighing the alcohol burner before and after combustion. And then they give us some information. And this is one of those problems that you're also learning how to read lab data. So from the data from the experiment are given in the data table below. And you have to be able to understand what you're all seeing. So the mass was combusted. It's 0.55 grams. You get the mass of water heated, initial and final temperatures, and then they give you the specific heat capacity of water. So you allow your equations and your equation sheets to help you with this. But letter A. It says calculate the magnitude of the heat energy in kilojoules absorbed by the water. Assume that the energy released from the combustion is completely transferred to the water. So to me, the minute I see specific heat of water and maybe temperatures, this leaps out to me as Q equals MCAT. Okay, because that Q is heat. So let's talk about this. This is just about the water. So the water weighed 125 grams. The specific heat capacity, 4.18. And the change in temp is going to be my 51 minus my 22. So I'm going to squeeze this in. And my final answer will be 15,200 joules. Make sure you answer the question the way it's asking. It's asking in kilojoules. So I'll have 15.2 kilojoules. And that would just be a point on your exam. All right, so we get the letter B. And these kinds of problems are ones that confuse students quite a bit. It is simply converting, and it's about units, but you have to understand what you need to start with and how you need to end. It says, based on the experimental data, if 1 mole is combusted, how much heat in kilojoules is released? Report your answer with the correct number of sig figs. So it's very important to understand how many sig figs you should be using and how you track that all. So to me, you got to keep insight in mind what you're talking about, and what we're talking about is you are discussing 1 mole, right? That it's wanting to know how much energy comes from the combustion of 1 mole. So let's start with 1 mole, and let's move this over a little bit. All right, so I let units be my guide, right? If I'm allowing that, everything else is going to work out so much better. So the trick of this is understanding something, that you are working in grams. You were combusting a certain amount of grams. So no matter what, I need to put moles on the bottom here. And if you realize that, I mean, if you start with moles, you're going to have 1 mole there. You add up the molar mass of the compound, and you find out that it's 60. And now I'm in grams. So how do I finish this off? Well, the only energy that I have here is 15.2 kilojoules. If the question's asking for the answer in kilojoules, I'm going to have that as my final answer. Well, what does that equal? What does that equal? Well, that energy is related to the entire reaction. Well, that energy was related to 125 grams of water, but I'm not talking about water. So what else am I talking about? I'm talking about this compound right here. And what's the mass? That. So for every 0.55 grams of C3H7OH, it releases 15.2 kilojoules. So that's how we get to our final answer. And this is very tricky. Initially, we would get 1661 kilojoules. Proper sig figs. Okay, let's quickly discuss that. 1 mole is more of a definition, okay? Now, I probably shortened this up. That is based off of me. That's on the periodic table. I could have written anything I wanted. So what is the number that's dictating this? A piece of data that was given to me. So I can only give it in 2 sig figs. So it's going to have to be 1,700 kilojoules. And that is really important. You get a point if you write that correctly. So it went out of its way to, the problem went out of its way to talk about that you need the right number of sig figs. So there probably was a tiny trick that you have to recognize if you're doing that correctly or not. Final question on this problem. It says a second student performs the experiment. Okay, they're going to use the same amount of water, it says, for the same initial temperature. They use the same fuel, but it's contaminated with water. So it's not pure fuel. Okay, but it's mixed together. Miscible, meaning it's mixed. The difference in the mass of the alcohol burner before and after is still 0.55, with the final temperature of the water in the beaker heated by the alcohol burner in this experiment may be greater than, less than, or equal to the final temp of the water. Because the fuel, quote unquote, that was burned was not pure alcohol or pure fuel C3H7OH, and some of the mass that was lost was water vaporizing, which would not give off heat and transfer heat to my water, it should be less than. It should be less than because I have a less of my C3H7OH that was actually burned. And that energy, when burning that, the combustion, would not transfer into my water. So that is why, even though it had the same mass change, some of that mass change was water vaporizing, which does not give off the heat that C3H7OH would. Moving on to our next question, this jumps out as a kinetics problem. And we're given many graphs. It gives us an equation of C4H6, and it's converting to C8H12. It says at high temps, the compound C4H6 reacts according to the equation above. The rate of the reaction was studied. 2 different trials, each with a different starting concentration, were carried out. The data were plotted in 3 different ways. So this should look very familiar. We have concentration here on the left. We have natural log of concentration, and then we have inverse of concentration. So first question. We're going to scroll down a little bit. It says A, for trial 1, calculate the initial pressure in ATM in the vessel at 625 Kelvin, assuming that initially all the gas present was C4H6. Whenever I'm being asked pressure and they're giving me temperatures, I have to think PV equals nRT. So I want pressure, I want temperature, and they're asking for trial 1. So if you go up to trial 1, which is the circle, this is concentration. So this is 0.020 moles over liters. This is the leap of faith you have to take. What this is saying is that many moles in 1 liter. Well, wait a minute. Moles are N and liters are volume. So now I have my P, T, N, and V. So now I can actually answer this question. So it's going to be pressure equals nRT over V. I have 0.020 moles. Put in my R value. Put in my T. And my volume is just going to simply be 1 liter. And what a nice number this gives me. 1 ATM. And that'll be 2 points, 1 for the setup, 1 for the correct answer. B, using the data plotted in the graphs to determine the order of the reaction with respect to C4H6. So we look at all this, and what we understand is the order correlates to our time, over time, the data versus concentration, natural log, or inverse concentration. And the one that makes a straight line gives us that order. So this is 0 order right here. As a reminder, that's concentration. This is 0. Natural log is always first order. And inverse of the concentration is always second order. And it appears that I have a straight line for my second order. So that is what we will deduce. So it's going to be second order. And doesn't ask for a justification or anything like that. So that is all that we would need. Letter C. They say that the initial rate of the reaction in trial 1 is 0.001 molar per liter seconds. Calculate the rate constant, which is K, for the reaction. Okay, there are 2 ways you could do this. You could use the integrated rate law that is on your orange sheet, or you could just use a rate law. So if I actually ask for the rate law, this would be my equation. Because this is second order, that's why it's there. Well, look what this does for me. The rate they gave me was 0.0010. I don't know K because that's what I'm being asked. The initial concentration is still what I had before. And that is to the second power. That will roughly be 2.5. And then The units are always one less than the overall order, although it doesn't ask for units, surprisingly enough, and that'll be 2.5 liters over moles seconds. Otherwise, you could do your units as such. Those are the other way that you could write your units. So I used the rate law. I thought that was the easiest way to do that. So that is how we could do a kinetics problem that looked much more daunting than it actually was. Our next question has just an A and a B. And what it shows you is that a net ionic equation, and the net ionic equation is basically between this very complicated polyatomic ion that we abbreviate ADTA, 4 minus, and it's reacting with barium nitrate, which the barium is all that's going to react. And then they give us a K on the right side. So A, considering the value of K for the reaction, so they're hinting towards something, determine the concentration of the BA, EDTA, 2 minus, so the products, in the 100 ml solution. Justify your answer. Okay, let's look at this for one moment here. If these are my two reactants, I have 0.3 molar, 50 mils of 0.3 molar of the EDTA, and then I have 50 mils of 0.2 molar of the BaNO32. So equal volumes, one's 0.3, one's 0.2, and the BA is a 1-to-1 ratio. So they're both equal. So right away, this value is my limiting reactant because it's going to run out because I have 0.2 versus 0.3. I'm going to run out of the 0.2 before the 0.3. So that's actually the key part to that. So if it's actually asking for concentration, what I would say is I had 0.2 molar of the BA, and now it is in a 100 ml solution. Sorry, initially it was in a 50 ml solution. Right? So that would be 0.01 moles of my BA. Well, it's a 1-to-1 solution, or 1-to-1 ratio, so that's actually going to be of my product as well, because it's a 1-to-1 ratio. And then I just put it over the new volume. And that would be my answer. Why does it say, I skipped this over, but considering the value of K, this is huge. So because of that, I can assume that all of this basically makes all of that. And that was the one missing part in my initial explanation. So because it said consider the K value, you can see that it's so large, I can assume all of my initial amounts will basically become products. Second problem can sound kind of confusing. Solution is diluted with distilled water to a total volume of 1 liter. So we have basically diluted this 10 times from the original volume. After the equilibrium has been reestablished, is the number of moles of Ba2 plus present in the solution greater than, less than, or equal to the number of moles of Ba present in the original? To me, what I read is, oh, so it reestablishes equilibrium. So now I'm going to decide whether or not it's going to the right or going to the left, because it wants to know if I'm going to have more Ba2 plus. So the minute I say which way is it going or where am I at, that is Q. Okay, and if we talk about this as Q, this would have been initially the relationship, and I don't even need to have that full values to get this right. This is what I know. If I dilute this, I basically am diluting this by 10. Right? That's what's happening. So ultimately, my value of my Q will be 10 times my initial K. What does that mean? Well, what that means is that my Q then is going to be greater than my K by 10 times the amount. So that means if I think of K here and now my Q is larger, it's got to drive back to reach equilibrium. Well, I'm driving it back to the left, so I'm going to make more. So the answer is that it's the Ba2 plus is going to be greater than the Ba2 plus with the 100 milliliters versus the liter solution. So that's a tricky mathematical relationship, but the K will be larger 10 times the amount from the liter to the 100 milliliters. And that concludes that short problem. All right, our fifth problem is a lab problem, more or less. It says a student is given 25 ml sample of an unknown monoprotic acid and asked to determine the concentration by titration. The student uses a standardized solution of NaOH, a burette, a flask, an appropriate indicator, and other lab equipment necessary. A, the images below show the burette before the titration begins and at the end point. What should the student record as the volume of NaOH delivered to the flask? Okay, so this is just understanding that, like, this value right here, if this is 37 as it shows and this is 38, that when it's halfway down, it's not below 37. Okay, so what we just need to do is make sure we recognize how much we see. So if you look at this one, you always want to estimate the last value. So this is about 5.65 milliliters. And the other value is 37.30 because the meniscus is on the line on the third one. And in this one, it's between the lines. So that's why we get a 5. So the question was, how much volume was delivered? We simply subtract the final minus the initial. And we get 31.65 milliliters. Letter B, based on the given information in your answer to part A, determine the value of the concentration of the acid that should be recorded in the student's lab. Well, because this made it to the endpoint, that means an endpoint means that I have moles of my acid equals moles of my base. Well, how do you do that? It's MAVA equals MBVB. And if people forget why that works, is that molarity is moles over liters, and then volume is liters. So what's left? Moles. Moles. So we're going to fill in what we know. It's wanting to know the concentration of my acids, so I don't know that, but I do know all the other information. So I know the volume of my acid, which we determined. Let's find it. 25 milliliters. And I can keep it in milliliters because it's going to cancel out. My molarity of my base was 0.110. My volume, which I just did, was 31.65 milliliters. Had to find it. So when it's all said and done, my concentration of my acid is 0.139 molar. All right. Final problem on this one. It says, in a second trial, the student accidentally added more NaOH to the flask than was needed to reach the endpoint, and then recorded the final volume. Will this error increase, decrease, or have no effect on the calculated acid concentration for this second trial? Justify your answer. Okay, so this is an error problem. So what you need to do is think about how that affects your answer. So what is it doing? It physically is saying which value in here in the MAVA equals MBVB is affected. It said that it was a larger volume and it was recorded as such. So this value is increased. So you could simply literally plug in a larger number. Like you can make up a number like 32 or 35 or whatever you'd like. And then you could recalculate it. So if you put a larger number in there, what would it do to my molarity? Well, the answer is the error would increase the calculated acid concentration. So the acid concentration would increase. And why? Because it would appear that it would take more more base to equal the acid that was in that Erlenmeyer flask on the bottom. But if you're questioning it, you could literally just say, okay, now I have 40 mils. let me recalculate it, and then you can compare your new MA to the one that you already calculated, and you could have figured it out that way. So that's how you work a very simple titration problem. Our next problem has another lab setup, and it shows a reaction happening in a test tube over a Bunsen burner, and then we're collecting a gas through water displacement, and the gas ends up going up this tube, and we collect some data from it. So it says ethene may be prepared from using a solid catalyst. It talks about the synthesis. It gives you an equation. It gives you an enthalpy. It gives you an entropy. It says a student added the 0.2 gram sample of the C2H5OH, so that's ethanol, to a test tube using the setup shown above. The student heated the test tube and waited until it all evaporated. Gas was generated. When the reaction stopped, the volume of the gas was collected. And then it gives you a bunch of data. And then they give you a little extra something. The vapor pressure of water at 305 is 35.7 torr. All right, what does that all mean? So A, calculate the number of moles of C2H4. I, that are actually produced in the experiment and measured in the gas collection tube. And double I, that would be produced if the dehydration reaction went to completion. So let's talk about one at a time. So if you were given volumes and pressures and temperatures, that's kind of screaming PV equals nRT. Ideal gas law is what is presently happening right now, what is currently happening. The one thing we need to talk about quickly is this idea of water vapor pressure. So when something is collected through water displacement, there's a certain amount of vapor pressure that is coming off of the water. So what it's saying in this problem is that the total pressure, which they're saying is 0.822 atms, all right, is all of that inside the tube. Well, if you notice now what I've written is this is what's actually happened, and this is an application of Dalton's law of partial pressures. So what we want is this, the pressure of C2H4, and then they gave us the pressure of water. Now they did a little trick with us that they have it in torr, and we have a pressure in ATM. So we need to do a little conversion here. So if I have 35.7 torr, what is that in ATM? For every 1 ATM, I have 760 torr. So if that's the case, now I can plug that in to my water pressure. So I subtract those two, and my vapor pressure, or sorry, my pressure of my ethene would be 0.775 atms. Now I have my pressure as well. Now I can find moles. So N equals PV over RT. The pressure is what I just figured out. The volume of my gas was stated in the problem. My R value. And the temperature. So the moles would come out to a decently small number. So you get 1 point earned for calculating the actual pressure and how I did that, and then 1 point earned for the actual moles. Now, what's confusing about this is this was letter I. Double I. It says that would be produced if it went to completion. And if you're wondering, well, how do I know if it went to completion or not? Well, stoichiometry, not an ideal gas law, which is using the actual amounts that is present, I have to now ignore how much volume was made. And if I started with a certain amount, which was 0.200 grams, let's move this over a little bit, of C2H5OH, by 0.200 grams of this, I want to know moles of this. So that now is just stoichiometry. So get into moles, 46.1 grams. And then it appears that it is a 1-to-1 ratio. So we calculate that out. So you should expect that you're going to make more because it asks for it to go to completion. Letter B. It says calculate the percent yield in the experiment. What is percent yield? It's actual over theoretical, or how much you made over how much you should have made. Well, I made 0.0026 moles of the gas. I should have made 0.00434 moles of the gas. So it's simply what was actually made over what should have been made. You divide those two, you turn it into a percentage, and the percent yield is roughly 60.8%. All right, letter C. So they reset the problem slightly. It says, because the dehydration reaction is not observed to occur at 298 Kelvin, the student claims that the reaction has an equilibrium constant less than 1. So translation, K is less than 1. C, do the thermodynamic data for the reaction support the student's claim? Justify your answer, including a reaction for G for the reaction. Okay, so they give me an H and an S value. So you should be thinking about an equation, change in G equals change in H minus T change in S. Let's talk about what else this actually means, is that my K is less than 1. So that means the reactants are favored, not the products, right? Because K is products over reactants. So let's see how those relate to each other. So I'm going to use this equation right here. And I'm going to plug in my values. So I'm going to plug them in right now. So plugging them in, I didn't want to go up and down, so I'm sorry, but I plugged them in like this. One big thing to notice is that you need to have the same units. So if you go back up to your S, is that this was initially in joules and this is in kilojoules. They need to be in the same unit. As long as they're in the same unit, it works out. So I get my calculation, and change in G would have a final answer of approximately 8.0 kilojoules per mole. So does that support the answer? Because change in G is positive, it is non-spontaneous, or meaning that the reaction is actually going to be going to the left, or the reactants are favored, and that K is less than 1 reinforces that same idea. So, yes, the data supports the student's claim. All right, let's scroll down. Letter D, the Lewis electron dot diagram for C2H4 is shown below in the box on the left. In the box on the right, complete the Lewis electron dot diagram for C2H5OH by drawing in all the electron pairs. All right, so this is complete change in pace. If it's between an atom, you do not need to be putting dots. You could be putting lines. So we know that H's all bond once. And my suggestion is bond everything once. And then you should realize that my oxygen needs 2 extra dots. So you just get a point for doing that. So that's a huge change of pace. We go to letter E on that. And it says, what is the approximate value of the COH bond angle in the ethanol molecule? So they're talking about this angle right here. All right, a Lewis electron dot diagram has nothing to do with angles. So if you look at that and you think linear, it has nothing to do with the geometrical three-dimensional relationships. It's just showing the relationships of the bonds to the lone pairs. So what we need to do is come up with a bond angle. The easiest way to do that is to count the electron clouds. So around the oxygen, because that's my center atom, I have 1, 2, 3, 4 clouds. So if you know a little bit about molecular geometry, I'm just going to do this generically, but I'd have my oxygen. This is how the four clouds fill a space. I could be putting the H here, let's say, and the C right there, and here are my lone pairs. This is a tetrahedral as a parent geometry. So initially, a tetrahedral has a 109.5 degree shape. Technically, if you've learned a lot about molecular geometry, is that every time you add a lone pair, it reduces it by about 2. So this is approximately 105 degrees because this is a bent shape. The actual geometry is bent. So I would go with the 105 degrees for my angle. Our final question brings us back to the experiment, but never underestimate the idea that letters above may help in aiding an answer. And I think that letter E helps us, letter D and E helps us a little bit with this. During the dehydration experiment, C2H4 and unreacted C2H5OH, or these two, pass through the tube into the water. So now they're both in the water. The C2H5 was quantitatively collected as a gas, so this is a gas. But the unreacted C2H5OH was not. So what that probably is, it's in solution. So I'm just going to say it's AQ, or it's in solution. So it's in the water. Explain this observation in terms of intermolecular forces between water and each of the gases. Okay, so we know that water is extremely polar. It has the ability to make a hydrogen bond with other compounds, or at least a strong dipole-dipole attraction. So because water is polar, molecules and compounds that dissolve in it are usually polar. So those that are staying in solution are more polar than compounds that are not polar. So when you look at these two shapes, this is very nonpolar. It's very symmetrical. Whereas the other compound is not. It is very polar. So my argument would be is that because of the hydrogen bonds, they would be extremely attracted to the hydrogen bonding in the water, and they would increase the interaction between the ethanol and the water, and that's why it would stay in solution. Whereas the ethene, which has basically LDs versus hydrogen bonding, would not have much, if any, interaction with the water, and thus would come out of solution, and that's why we were able to collect it as a gas. And that completes that problem. All right, this brings us to another acid-base problem, which will deal with equilibrium. So basically, it is talking about a compound that is in soft drinks. We have a stock solution of it, and we are going to titrate it with some acid, some HCl. And we're going to use an indicator and a pH meter, and they give us the Ka of the acid as well. So it says A, write the net ionic equation for the reaction between the KC6H7O2 and the HCl. So whenever I'm reacting anything in these problems, I always kind of think about what I'm given. And I know HCl is a strong acid. So strong acids break apart. And the thing that is most important with a strong acid is the H+. So I have to write H+. So then I look at this compound, and this is a salt. And a salt breaks up into two parts, a cation and an anion. So what I do is I just logically think to myself, well, what can bond or react or interact with my H+? Well, opposite charges. So I have to take the C6H7O2 minus ion. I didn't know that before I started. That must be what I have to grab. And then it's going to make the HC6H7O2 because that's how that interaction is going to go. So that would be my initial equation. Our next problem, it says a total of 29.95 milliliters of my acid is required to reach the equivalence point. Calculate the concentration of my KC6H7O2. Well, it says that I use 45 mils of my solution. So I simply have to say M1 V1 equals M2 V2. And that will get me my answer. So it'll be 0.832 molar. 1 point is earned for realizing that you needed the multiply on the left, and then 1 point is earned for the molarity. All right, the pH at the equivalence point of the titration is measured to be 2.54. Which of the following indicators would be the best choice for determining the end point of the titration? Justify your answer. We want an indicator that changes color at a pH that helps us know when that endpoint is. And an endpoint is when, just so we remember, is when my moles of my acid equals the moles of my base. That's very important. So the whole goal, by the way, of the endpoint is that you want an indicator to be plus or minus 1 from that pH. So the only logical choice, because you want it around that range, is if the pKa is 2, that'll match up with the pH. I want thymo blue because it's at the same point that that color change is going to happen for the pH. So letter D leads us into that. Calculate the pH at the half equivalence point. Well, the half equivalence point is simply the pKa. So the pH equals the pKa at the half equivalence point, and that's something you need to know. So if I have the pH already and I know that it equals pKa, that's a pretty simple relationship. It's going to be negative log of my Ka. I go to the top of my problem, and they gave me a Ka of 1.7 times 10 to the negative fifth. The pH would be 4.77. Okay, now we get the graph, which is kind of a nice change of pace on an AP chemistry exam. It says the initial pH and the equivalence point are plotted on the graph below. So it's very important. We need to put the initial pH. We need to put the equivalence point on there. Accurately sketch the titration curve on the graph below. Mark the position of the half equivalence point with an X. So we need 3 points. So that's very, very important. An understanding of titration curves is very important on this. So first off, they are already giving us an initial amount. It's right here. They gave us that, and they're actually giving us the equivalence point is plotted as stated before. So if you don't understand titration curves, you might draw it like this. That is the sign of a strong acid with a strong base. So what we need to do is make sure that we are showing a weak, we have weak components in here, not strong. So let's put our X in here, which was the pH of 4.77, and we need to know the approximate volume. So why is it a half equivalence point? Because if the equivalence point's at 30, that means the half equivalence point is at 15, and that's really important. So my X is going to be at 4.77, which I just stated, and now I need to make a titration curve that resembles a weak base with a strong acid. So you start increasing the slope, and then it starts to decrease, and then it comes down. And we don't need to go any further than that. So you actually get a point. You get credit for having that sharp slope that then decreases as it goes through that buffer region. You don't have to mark this, but that is what we call the buffer region, because the pKa or the pKb, usually pKa, is always in the center of my buffer region. Final question on this problem. It says the pH of a soft drink is 3.37 after the addition of KC6H7O2. Which species, the HC6H7O2 or the C6H7O2 minus, has a higher concentration in the soft drink? Justify your answer. The trick and the tip that this problem is trying to give you is that it's not asking for an actual numerical answer. It's a relationship. So if you can try to understand if there's a ratio between these two species, we just have to find that ratio. And there is. It's the Clausius-Clapeyron, or you can just use the Ka expression. We could do a lot of things. So this is the way I'm going to attack it. I'm going to utilize the equation that looks like this. Although that does not matter. I'm going to use this relationship. So actually the balance equation doesn't matter. So what was the pKa? Well, we already had figured that out. 4.77. It says that the pH is 3.37. And then I have this relationship right here. So what I want is I wanted to solve for the acid over the base. So if I calculate this out a little bit, what I get is this relationship. I change the acid and base to the actual formulas. And that is a ratio. And what is it saying? This relationship between the base and the acid is 0.247. So that means that I have a larger amount of my acid than I do my base. So that is how I could justify my answer. So that species of HC6H7O2 is greater than the C6H7O2 minus. The next problem works with some food blue coloring, and it's tested on absorbance over time. And again, because of the y-axis labels, this is clearly a kinetics problem. So I have absorbance, which is like a concentration, natural log of absorbance, and inverse of absorbance. So we'll break this down as we go. So letter A, it says, based on the graphs above, which is the order of the reaction with respect to the blue food coloring? As we've stated before, you are trying to find the one that makes a linear relationship. So clearly this equation, or this graph, is a linear relationship, and it's natural log of absorbance. So you need to understand that that is first order. It doesn't have to be in order on your problem, but it is. This would be a second order, and this would be a zero order if it was chosen. And then the middle one is first order. So that's all that first one was referring to. Letter B, kind of lengthy, but quick in answering it. The reaction is known to be a first order with respect to bleach. In a second experiment, the student prepares the solutions of food coloring and bleach with concentrations that differ from those used in the first experiment. When the solutions are combined, the student observes that the reaction mixture reaches an absorbance near zero too rapidly. In order to correct the problem, the student proposes the following three possible modifications in the experiment: increasing the temp, increasing the concentration, and increasing the concentration of the bleach versus the food coloring. Circle the one proposed modification above that could correct the problem and explain how that modification increases the time for the reaction mixture to reach an absorbance near zero. Well, if you understand the problem, it's bleach is reacting, and we are testing the absorbance that the food coloring has. So if it's reaching equilibrium too quickly and we can't test it, that means we are losing or don't have enough of our food coloring to test its absorbance. So by increasing the concentration of the food coloring, this will in essence slow down the reaction, and there'll be more time for the bleach to oxidize the additional blue food coloring. So it will slow it down, and it'll give it more time for that process to occur. Finally, It says in another experiment, a student wishes to study the oxidation of red food coloring instead of blue with bleach. How would the student need to modify the original experimental procedure to determine the order of the reaction with respect to the red food coloring? Okay, if you're unsure of a question like this, it's important to go back to the setup. And in the problem, it says, and it lays it out, that blue food coloring can be oxidized by bleach to form a colorless product. It says a student used a spectrophotometer set at a wavelength of 635. You have to try to remember that we have wavelengths from 700 to roughly 400 nanometers, is that the spectrophotometer has to be set at certain wavelengths to study certain colors. So what we would have to do is change the wavelength. It is not asking you to come up with a value. You just simply have to understand that you need to change the wavelength of the spectrophotometer if you're going to test a different color for absorbance. All right, and the next problem changes gears back to acids and bases and equilibrium. So it gives us an equation. Propanoic acid is a carboxylic acid that reacts with water according to the equation above. At 25 degrees of pH of a 50 ml sample of 0.2 molar propanoic acid is 2.79. We're going to need that later. A, simple but difficult if you don't remember. Identify a Bronsted-Lowry conjugate acid-base pair in the reaction. Clearly label which is the acid and which is the base. You honestly have two answers for this. So first, you got to understand there's pairs. Right, those are the pairs. So acids give away H's. They donate H's. So this is an acid, so this must be the conjugate base. Bases accept H's. So you could have either said the acid, the conjugate base, or the base and the conjugate acid. Either one of them is appropriate. So that was letter A. Letter B, determine the value of Ka for the propanoic acid. And that's all it says. So if you can solve for Ka, that means you must know enough other information. So first, let's break this down because it doesn't feel like you have enough information in the beginning. So what we need to do is understand what we're given here. So it's going to be products over reactants, and you only are using the aqueous species. So what you need to realize is that you must have enough of that information given to you. So if you don't know, maybe a icebox would be appropriate. So I'm going to set that up. All right, so here's my icebox. And let's see what we have been given here. So it says that I have 0.2 molar of my initial amount here. And then it says that it is 2.79 for my pH. pH is always the equilibrium of my H+. So concentration of H+ equals 10 to the negative pH. So that will be 1.6 times 10 to the negative 3. And then that's all the values I have. You need to understand that if you're finding a K, that means you must know everything on this line. Well, if you have an initial on one species and you have a final on another, all the work is done for you because this is plus X, this is minus X. So X must equal 1.6 times 10 to the negative third. So you would take 0.2 minus that value. This will be the other value of X. So let's plug that in. So it'll be 1.6 times 10 to the negative 3 times 1.6. I'm using the K value from above. And then I put this below that value. And my Ka equals roughly 1.3 times 10 to the negative fifth. Okay, let's look at letter C, because it kind of changes just a little bit. For each of the following statements, determine whether the statement is true or false. In each case, explain the reasoning that supports your answer. The pH of the solution prepared by mixing 50 mils of a 0.2 molar CH3CH2COOH with a 50 ml sample of 0.2 molar NaOH is 7. All right, first, my gut feeling right away is that this is a strong base and this is a weak acid. So only strong acids and strong bases that are mixed together will basically ever be 7. But you probably need to show more than that. So if you were going to combine these, first off, a weak compound is always added to just the portion that matters for a strong base. So that's OH. OH, they're equal amounts, so it's going to completely consume and become OH plus the conjugate base that we just talked about. Well, after these both are consumed and drives and makes this heavy amount, what happens is it has to dissociate. So it's going to flutter back the other way. This is actually remnants of an equivalence point. So if you're going to come back the other way, it's going to be making OH minus. So it will be basic. So this is false. Double I. Says if the pH of a hydrochloric acid solution is the same as the pH of a propanoic acid solution, then the molar concentrations of the hydrochloric acid solution must be less than the molar concentrations of the propanoic acid solution. You don't need to calculate this. It's just saying, do you need less HCl than the propanoic acid to reach the same pH? Well, if this is a strong acid, it completely 100% dissociates, while a propanoic, which is a weak acid, does not. So the answer is true. You would need a lot less because more of it will always go to the product side in a strong acid compared to a weak acid. So that would be my justification for that it dissociates 100%, so you will have less of a concentration to reach the same amount of product. Final two problems. It sets up a new scenario. It says a student is given the task of determining the concentrations of a propanoic acid solution of unknown concentration. A 0.173 molar NaOH solution is available to use as a titrate. The student uses 25 mils volumetric pipette to deliver the propanoic acid solution to a clean, dry flask, so we know it's exactly 25 mils. After adding an appropriate indicator to the flask, the student titrates the solution with the NaOH, reaching the endpoint after 20.52 milliliters of the solution. Base solution has been added. B, calculate the molarity of the acid. So hold on. Let's make sure we understand what's happening here. So this is my burette. What it's saying is I had exactly 25 mils. Let's call it my weak acid, so I don't have to write out propanoic acid. I had my strong base right here, and I used 0.137 molar, and it said that I dropped 20.52 mils of my base. So it says calculate the molarity of my propanoic acid. This looks like M1V1 equals M2V2. So I have M1 V1 equals M2, which is going to be my acid, V2. So the molarity of my acid would be 0.142 molar. So that would be letter D. Letter E. The student is asked to redesign the experiment to determine the concentration of a butanoic acid solution instead of a propanoic acid solution. For butanoic acid, the value of pKa is 4.83. The student claims that a different indicator will be required to determine the equivalence point of the titration accurately. Based on your response to part B, do you agree with the student's claim? Justify your answer. Okay, so let's see what the heck we said in part B. Part B was determine the Ka, which was 1.3 times 10 to the negative fifth. So Ka equals 1.3 times 10 to the negative fifth. Well, pKa, so then we got to find the pKa of this. So pKa equals negative log of 1.3 times 10 to the negative fifth. So for the propanoic acid, it's 4.89 compared to 4.83. The general rule is with an acid is that its pKa and an indicator whatever the pH or pKa of an indicator would be, is it just needs to be roughly about plus or minus 1 from that value. So the difference between 4.89 and 4.83 is such a small amount that the indicator that you used in the propanoic acid would be the same as the butanoic. There's not enough difference. So I disagree with the student's claim because the pKa values are so close. So you would use the same indicator. This next problem can be extremely confusing, and you can approach this in a couple ways. So it says aluminum metal can be recycled from scrap metal by melting the metal to evaporate impurities. So I want to go from a solid to a liquid. Well, that's a phase change. So it says, A, calculate the amount of heat needed to purify 1 mole of aluminum originally at 298 Kelvin. By melting it, the melting point of aluminum is 933 Kelvin. The molar heat capacity of aluminum is 24 joules per mole Kelvin, and the heat of fusion of aluminum is 10.7 kilojoules per mole. This is how I envision this. I think of a heating curve. So we had this, where we have a solid, and then it's a solid to a liquid, and then you have a liquid, and then it's a liquid to a gas, and then you just have a gas. Well, what we're doing is basically trying to just get it to a liquid. So what I need to do is get it to that point right there. So what we did, if I expand this out, is that we talked about things like this. This is heat of fusion right here. And this is Q equals, oh, I'm sorry, wrong way. This is heat of fusion, which is the change from my solid to my liquid. And to increase the temperature, it's Q equals MCAT. Okay, so we need both of these. We're going to add these together. So first, I need to raise the temp, and then I need to do the phase change. So we're going to do one at a time. So here we go. So it said I have 1 mole. So basically, I mean, I could say that I have 27 grams and then divide by it right away. So basically, I have a mole of it. And the reason why is that I know that I have mole here. So I have 1 mole. We're going to change that just a little bit. I have 24 joules per mole Kelvin. And then change in temp is going to be, I'm going to 933 Kelvin from 298 Kelvin. So that's about 15,000 joules, which equals 15 kilojoules. All right, my heat of fusion, which is my phase change, says that the heat of fusion is 10.7 kilojoules per mole. Well, I have 1 mole, so I wouldn't have to do anything. I just want to show something about this, is that if this was per mole and then you had a certain amount of grams, or you had half a mole, well, then you'd have to multiply it. But I have 1 mole already, so I have 1 mole. So that's going to be 10.7 kilojoules. So, translation, it takes 15 kilojoules to raise the temp, and then 10.7 kilojoules to convert it from a solid to a liquid. So it'll be 25.7 kilojoules, or if you round, it'll be 26 kilojoules. Okay, the second part of this problem, and why this truly does fall under thermodynamics, is first we are using Q equals MCAT and enthalpy of fusion. Now it says the equation for the overall process of extracting aluminum from aluminum oxide is shown below, which requires less energy. Recycling existing aluminum, which is what we just did in letter A, or extracting aluminum from aluminum oxide. Justify your answer with the calculation. All right, all the information that we need is given right here. So it's very important. This is per reaction. So this reflects each of those coefficients. And what are we talking about? We're talking about aluminum. So what I have here is I have 2 moles of aluminum. And what it's saying is that 2 moles reflects the fact that it takes 1675 kilojoules per 1 mole of this reaction. So we need to utilize our information here, and I have 1675 kilojoules per mole of a reaction, of one reaction. This is very important to kind of try to balance out my units here. I have one reaction for every reaction. This is reflective of each of my coefficients. I have 2 moles of my aluminum. Right? And you can think of it as moles of reactions, or you could get rid of the moles and just say per reaction. So what this will do is cut this in half, and I have 837.5 kilojoules. So it asks basically which requires less energy. Well, this one requires 837.5 kilojoules, while the first one required 25.7 kilojoules. So clearly, the recycling requires less energy than extracting the aluminum, which is from our letter A than from letter B. Our next problem talks about half-lives. So we have a cis and trans 2-butene, and you can just see that it just changes where my carbon chain is surrounding and orientated around my double bond. Either it's above it or one above, one below. And it's represented, the data is below in different conditions, pressure, volume, temperature, and then it has a half-life. A, the reaction is first order. Explain how the data in the table are consistent with a first order reaction. You need to recognize that it's talking about half-life, and it has half-life right here. So if you look up the equation for half-life on your equation sheet, it says that the half-life equals this value. So what do you notice is absent in my half-life equation? It doesn't have anything about concentrations. And concentrations can be considered pressure. So if you look at pressure right here, and you look at a change in pressure, you have 300 and then you have 600, the half-life change does not change. And it goes back to 300 and it's still 100, and then it's at 300 again. Oh, why did it go down? Well, temperature changed. Temperature can alter many things with a reaction, especially half-lives, because that affects the K. So that is why it is independent of concentration, and we change concentrations and the half-lives remain exactly the same. So that is the ultimate guide. So the half-life was unchanged when concentration was altered. Letter B. It says calculate the rate constant K for the reaction at 350. Include appropriate units with your answer. Well, if I'm solving for K, I'm just going to rearrange this. I'm just using it from above. So it's going to be 0.693. My half-life is 50 seconds. Include units. Well, there's nothing over seconds. So that it was just going to be my answer that I'm going to get from that calculation. And then inverse seconds. I just had to plug it in. Letter C, is the initial rate of the reaction in trial 1 greater than, less than, or equal to the initial rate in trial 2? Justify your answer. Never lose sight of what rate means. Rate is simply this. It's a concentration. So I could say of cis, or I could say, I'll just keep it at cis here. So, because that is my product, or my reactant. So all I need to do is basically plug in the concentration, which is like my pressure. So if I plugged in my 300 versus my 600, well, that second number is larger. So the trial 1 is going to be less than trial 2 because the concentration is less. So it's going to create a lower rate, just mathematically. Last question is a great question because it's really hard to sometimes explain things in words instead of drawing. So it says the half-life of the reaction in trial 4 is less than the half-life in trial 1, which is true. It's 100 versus 50. Explain why in terms of activation energy. Okay, so if you're thinking about activation energy, it looks like this. Okay, so if something's going to happen faster, that means all of a sudden it has a lower activation energy, right? That activation energy from start to finish is not as high, or it's lower. So what does that mean? All right, you have to have a certain amount of energy or a certain number of collisions that have to overcome this hump. Okay, so the temperature is higher in trial 4. So that means you could think of it as the kinetic energy is greater in the molecules. Because of that, there's a greater fraction of collisions that have enough energy to overcome that activation energy barrier. And that's why the rate is greater. So you can overcome that activation energy barrier because the kinetic energy is greater because of the increase in temperature of all those molecules, and that aids in those collisions. So temperature has a profound effect on the rate of any reaction. Okay, we're back on some equilibrium problems. So it says student prepares a 100 milliliter of a saturated solution of MgF2 by adding 0.5 grams of solid MgF2 to 100 mils of water. And it talks about how the saturated solution is analyzed, and F minus in the solution is 2.4 times 10 to the negative third molar. I. Write the chemical equation for dissolving solid MgF2 in solution. So you got to be careful. It does not, or in water, it does not mean to actually write the water. This is a KSP problem. So you're taking, it does not ask for states of matter, but I think it helps. You're taking a solid and you're breaking it apart into ions. So this is AQ, this is AQ, and then you got to make sure it's balanced. I have 2 F's on the left, so I need 2 on the right. So that is all I would need for that first part. And that is actually AI. A double I. It says calculate the number of moles of MgF2 that dissolved. Okay, this is very important because you know how much F minus dissolved. You can figure out how many moles of your MgF2 have actually dissolved. So what I would do first is utilize the numbers that I'm given. So I have 2.4 times 10 to the negative third molarity, so that's moles over liters, and this is of my F minus, okay? Now, eventually I'm going to need to get out of liters here, so let's just do that right away. So it's 1 liter for every 1,000 milliliters. I'm sorry, we need to get into moles. So I need to get rid of the liters. So I am using a 100 milliliter sample. My fault. And then now for F, for every 2 of these, 2 Fs, ultimately it's 2-to-1 ratio. Okay, so what you could do is just simply think of it this way, is that you could take this whole relationship right here and then simply say for every 1 mole of my MgF2, I have 2 moles of my F minus. And because of that, I am going to get a value. So 1.2 times 10 to the negative fourth moles of MgF2. Another way you could have thought about it is just figuring out the amount of Mg2 plus that dissolved, because that would be the same as saying the amount of MgF2 because it's a 1-to-1 ratio. Okay, so in theory, you could have said it just like that. So that could be of Mg2 plus. So double or triple I says determine the value of the solubility product. So you need to be able to just plug this in. If you don't know KSP, that means you need to be able to know the rest of it. So it did not ask this, but the expression would look like this. So I would plug the values in. So as I stated before, that number that I just determined was actually of Mg2 plus as well. So I would plug that in for my Mg2 plus. So an icebox sometimes is extremely helpful. So if you're thinking about the balanced equation, which I'm going to actually treat this as a balanced equation right here, is so at 0, 0, this is plus x, this is plus 2x. If you go up here, right, at 0, 0 plus 2x plus x, I had a certain amount at equilibrium, which was 2.4 times 10 to the negative 3 molar. All right, so if that's at 2x, x would only be half of that. So it's 1.2 times 10 to the negative third for my Mg2 plus concentration, not moles. So now I need to plug those into my equilibrium expression. And I'll get 6.9 times 10 to the negative ninth. So we shift to letter B. It says the beaker contains 500 mils of a solution with both Ca2 plus and Ba2 plus are present at 0.1 molar. A student intends to separate the ions by adding 0.2 molar of NaF solution, 1 drop at a time from a burette. At 25 degrees, the value of KSP for KF2. So what they're saying is when Ca and F combine, it makes a precipitate. And they're saying when Ba and F combine, it makes a precipitate. Okay, it's important to understand what's happening. So I have Ca2 plus and Ba2 plus floating around in this solution. And as I slowly drop my F, it's going to combine with both, and eventually one of them is going to precipitate out first. So which salt will precipitate first, the CaF2 or the BaF2? Let me try to write this out once. That might make more sense to you. So it's saying that for the CaF2, the KSP looks like this, and then this would be the equation. Okay. For the BaF2, it looks like this. Okay. So what it's asking is which one will precipitate out first. What you need to notice is that they said that both of these values were exactly the same. So it only matters about F. And if you're adding these both exactly at the same time, eventually these values are going to equal these numbers. What students have a hard time understanding is what does KSP mean? Is that when these two values equal the KSP exactly, there is no more of either ion that can fit in that solution. Any more, it will start coming out as a solid. Okay? So your challenge is which one, if you're starting to add F, you're adding it into solution. Actually, think of it as adding it going down. You're dropping it in a solution. Which one is going to reach that KSP first? Well, this number is much smaller than the other one. So that relationship is going to happen sooner. So the answer will be which one will precipitate out first. It will most definitely be the CaF2 because the KSP is so much smaller. So that is Bi. All right, moving forward, Bii. Says for parts Bii and Bii below, assume the addition of NaF solution does not significantly affect the total volume of the liquid. So the molarities don't change. I, because of the volume. Calculate the minimum concentration of F- necessary to initiate precipitation of the salt selected in part Bi. Well, we are simply going to plug it in to this relationship. So I have 3.5 times 10 to the negative 11th, which is my KSP. I was told that my concentration of my Ca2 plus was already 0.1 molar, and now I'm trying to find out the concentration of my F-. And don't forget, it is squared. So when it's all said and done, you get an answer. Well, let's just do a little bit of work here. I'll have that first. Right? I'll take the square root of both sides, and ultimately the amount of F- that would be needed to be added is 1.9 times 10 to the 5th molar. So that is how I would use double I. Oops. Triple I, calculate the minimum volume of 0.2 molar of NaF that must be added to the beaker to initiate precipitation of the salt selected in part BI. All right, this is just a simple relationship. So what it's basically saying, what is the volume of a 2 molar solution? So I don't know the volume that must be added to the initial volume that I had, or the solution that I had from the previous problem. So I have a concentration that I just determined, and I know that that is in a 500 milliliter solution. So when it's all said and done, it's roughly 4.7, let's say 5, times 10 to the negative second milliliters. So it's a very small amount, very small amount. Lastly, there are several ways to dissolve salts that have limited solubility. Describe one procedure to redissolve the precipitate formed in part B. So in part B, we had, and even if you chose the wrong one, we were saying that CaF2 is dissolving or it's not. Right? It's either precipitating or it's becoming an ion. So how do we cause it to redissolve? There are many ways you could do this. So if you're confused by this, we want to drive it that way. Well, one, just think about this. What if you added more water? If you just add more water, there's more space for it to dissolve. So you could simply just add more water, which would dilute it, and that would definitely happen. What's another way that we can usually increase solubility? We'd also increase temperature. So those are two things that come to my mind immediately, and those would probably be the easiest ones to talk about in your answer. Okay, this next problem has a bunch of data, and they give us an equation where they're taking MgO and they're adding HCl to it, and they're trying to find out the enthalpy change or the heat flow change. So A, which is the limiting reactant in all 4 trials, HCl or MgO? All right, so what you need to know is how much you have of each. So the HCl is based off of molarity. So basically, I have 1 molar, so it's 1 mole over 1 liter. And then I was using 0.1 liters, right? So that's going to be just 0.1 moles. Okay. For the MgO, let's use the maximum amount so we can see how that one works. So we either have 0.25 or we have 0.5. And it's saying that it's limiting reactant no matter what. So let's use the one that's the greatest. So I have 0.5 grams of MgO. And that's simple stoichiometry. And I have 0.0125 or 4 moles of MgO. So now we can simply just look at the equation. For every 2 of these, I have 1 of these. So you can pick either one. So I'll just do the 0.10 moles of HCl. And for every 2 moles of the HCl, I have 1 mole of my MgO, which clearly already you can see that's how much I would need, and I don't have even close to that amount. So MgO is my limiting reactant by far. It's not even close. Letter B says the data in one of the trials is inconsistent with the data in the other 3. Identify the trial with inconsistent data and draw a line through the data from that trial in the table above. Explain how you identified the inconsistent data. This is tricky. What do you have? The only data that you have, the results, is the temperature change. So I quickly crunched the numbers, and I got that this was a 1 degree change, this was a 4.1 degree change, this is a 2.1 degree change, and this is a 4 temperature change. And what I noticed was this is I'm either using 0.25. This is consistent, right? So that's not going to matter. So you're looking at the MgO. So it appears that when you're using 0.5, because both of these are using 0.5, it's around 4. And then when you use half of that, this one right here happens to be half of these other two, while this one being half of my MgO is not half of the temperature change of the other MgO that is double that value. So that is my rationale, that it is not half of the amount of the other temperature changes when the MgO is half the amount of the 0.5 that is used. So that is my change, is that when I doubled the MgO, it appeared that my temperature change doubled, except for trial 1. For parts C and D, use the data from one of the other 3 trials, not from the trial you identified in part B above, so we're not going to use trial 1. Assume the calorimeter has a negligible heat capacity, meaning that the calorimeter does not absorb heat, and that the specific heat of the contents of the calorimeter is 4.18, which is equivalent to water. Assume that the density of the HCl is 1 gram per milliliter. C, calculate the magnitude of Q, the thermal energy change, when the MgO was added to the 1 molar HCl. Include units with your answer. So this is screaming MCAT. And we can use any trial we want. So I'm just going to use trial 2. So be mindful that it said that the density is 1 gram per 1 mil. So right away, I am saying that the HCl is basically 100 grams. This is the specific heat capacity. And then my temperature change, I already figured that out, is 4.1. So I get 1,700 joules or 1.7 kilojoules. Letter D, determine the student's experimental value of change of H for the reaction between MgO and HCl in units of, and I'm sorry, this got cut off, in units of kilojoules per mole. That is really important. They are going out of their way to say that, kilojoules per mole. So what you have to do is realize that all we right now have is kilojoules, which is Q. Q is not enthalpy. Q is just heat. Enthalpy is the amount of heat per the amount of stuff, which is moles. So all you need to do is figure out how much you have. So that trial that we just did, I had 0.5 grams of MgO, right? And then I wanted, and I already did this work, but I'm going to just do it again. Right, I did this above. So now I need to take these two and divide them over each other. So I'm going to take enthalpy is equal to 1.7 kilojoules over the amount of stuff, the amount of moles I have of my compound. And I get a final answer of 140 kilojoules per mole. It is also really important to understand that if you're asked for a unit, you might be. If it's releasing energy into the water, that means it is losing it from its system, from the reaction itself. So it actually would be a negative 140 kilojoules per mole. Letter E, it gives us some enthalpies of formations for substances involved in the reaction, shown in the table below. Using the information in the table, determine the accepted value of change in H for the reaction. Okay, so right away you should recognize that all these values are from my balanced equation, which looks like this. And what we need to do is apply those numbers to each species in that chemical reaction. So that would look like this. So when you're given something like this, what you need to realize is it's asking for the change. So that's products minus reactants. So I'm simply going to take into account the moles of each one. So I only have one for each of my Mg and my H2O. So this is my reactants. And it's the sum of my reactants subtracted by the sum of my products. I mean, sorry, of my reactants. Those are my products. These are my reactants. And I know that I put the 0 there, but I'm trying to show why and how that 2 would be effective in my final problem. So my final answer then would be negative 151 kilojoules. So F goes off of this then. To finish this up, it says the accepted value and the experimental value do not agree. If the calorimeter leaked heat energy to the environment, would it help account for the discrepancy between the values? Explain. Well, let's just talk about this. This is the accepted value. So if you're even doing a percentage, this is the accepted value that we just had. And the one that we did over here was the experimental value. So I have less. So if the calorimeter leaked heat, does that make sense to the environment? Yes, because if it leaked heat, that means then that energy would not go into the water. So the heat flow and the temperature change that we were testing would not reflect that because it would have leaked out into the air, into the surroundings. So that is why this would be less than that number, because we weren't able to test it because that heat never made it into the water that we were testing for our temperature change. So we enter our final problem. We're given an equation on the top, and then it starts talking about an experiment. So a student designs an experiment to study the reaction between the NaHCO3 and the Hc2H3O2. The reaction is represented above. Student places 2.24 grams in a flask and adds 60 mils of the 0.875 molar of the acid. Student observes the formation of bubbles and that the flask gets cooler as the reaction proceeds. A, identify the reaction represented above as an acid-base reaction, a precipitation reaction, or a redox reaction. Justify your answer. All right, I want to break this down, and we're going to go into things that are obvious. A precipitation reaction would normally mean that we're going to produce a solid, most likely, and that does not exist on my products. So that is out. Secondly, a redox reaction is when I have two different compounds that are changing charges. And that usually occurs when you have elements that are by themselves and now they're bonded with something else. And in general, all of the atoms, and we could go through all of this right now, but are all acting as ions or are bonded in very similar ways. So what you eventually have to recognize is that this is an acid, so this is probably a base, and this is an acid-base reaction. All right, letter B. Based on the information above, identify the limiting reactant. Justify your answer with calculations. Okay, so what we need to do again is find out how many moles we have for each. So we're given this in two different ways. One of them we're given in grams, so we need to convert to moles using just a T-chart. The second one we're given as a solution. So that changes things just a little bit. So I was given a 0.875 molar solution, which is basically moles per liter. And then I need to multiply it by the volume that it was given to me in. So this is 60 milliliters, which is 0.06 liters. And I'm going to get 0.0525 moles. Okay, but this is going to be easy for us because it's both a 1-to-1 ratio. All I need to see is which one's going to run out first. And we can see that this, the NaHCO3, is going to be my limiting reactant. If it were not a 1-to-1 ratio, we'd have to take one of those answers and then compare using the mole ratio. All right, letter C. The student observes that the bubbling is rapid at the beginning of the reaction and then gradually slows as the reaction continues. Explain this change in the reaction rate in terms of collisions between reactant particles. Okay, these two have to collide for chemistry to occur. And then eventually when they collide, they are going to make CO2. With all reaction rates, it's the highest in the beginning because we have the most reactants. It's like a school dance. If you are trying to pair up and everyone's trying to find a dance partner in the beginning, everybody is available. Eventually, you're going to start trying to find a dance partner, and not everybody is available to dance with you, so it's going to take longer and longer, or eventually will not be possible for you to find a dance partner. So as the reaction continues, there is less and less collisions between the reactants because the reactants are becoming more and more consumed, and the concentrations of those reactants are dissipating. So the reactant concentration is going down, which causes the number of collisions between those reactants to decrease, and thus the rate of that reaction is slowly decreasing in that gas production. Letter D. In terms of thermodynamics, a reaction can be driven by enthalpy, entropy, or both. Consider that the flask gets cooler as the reaction proceeds. What drives a chemical reaction between NaHCO3 and HC2H3O2? Answer by drawing a circle around one of your choices below. So it is very important to understand each of these items. So when we're talking about this, enthalpy is about heat. Okay, so let's just talk about that. Entropy is about disorder. And then we can talk about both. For a reaction to drive forward, you want to increase disorder. Heat or energy, you want to release that energy. So you want to release it. So how do I write that? The reaction's going to slowly release that heat. So I guess for us, in all intents and purposes, we're going to feel that. The heat's going to increase in that reaction. So the key to this is two things. One, it gets cooler, and then here I go from 2 species to 1, 2, 3, and one of them is a gas. So definitely it's disorder. So now your question is it enthalpy as well? Okay, so it can't be enthalpy only, because entropy is definitely increasing. But the fact that it's getting cooler means it's absorbing energy, it's absorbing heat, and that is not the natural progression of a reaction. So it's going to be entropy only. So justify your selection in part D(I) in terms of change in G. Well, when you talk about change in G and then you throw out the words enthalpy and enthalpy, you have to be thinking about this equation. Well, for this reaction to naturally occur, I need G to be positive. But unfortunately, let's start over again. G needs to be negative, but H is positive. So for this to occur, I need my temperature is going to be constant. I need my change in S to be extremely positive. And the reason why this works is that I have created a gas, and gases are extremely disordered compared to solids and aqueous solutions. So the disorder is great enough to cause this reaction to still be spontaneous, causing the G to be negative. So that is my D(I) explanation. All right, we have to draw something in letter E. It says that the HCO3 ion minus ion has 3 carbon to oxygen bonds. 2 of the carbon to oxygen bonds have the same length, and the third carbon oxygen bond is longer. If it's longer, that means it's a single bond. Okay. Most likely. The hydrogen atom is bonded to one of the oxygen atoms. In the box below, draw a Lewis electron dot diagram or diagrams for the HCO3 minus ion that is or are consistent with the given information. The fact that they say that I could draw more, I'm starting to think this is a resonance structure. So I always think about the fact that carbon is my center atom. All right, hydrogen has to be on the outside. So if there's 3 O's, it'd probably be something like this. Okay, and then what I'm going to do, I'm just going to pick one of them. I'm going to put an H on the top. It could truly be almost any of them. All right, and now I want to make sure, it says the Lewis electron dot diagram, so I want to make sure everything has a dot. So if it's saying that some of the atoms are not as long as others, I can't break octets, so O's usually only bond twice. But carbons bond 4 times. I only see 3 bonds. So I'm assuming there's a double bond there. They kind of tipped their hat when they said, or their hand, that there might be more than one drawing. And a resonance structure usually has a double bond that is moving around. So if I redraw this again, I'm going to assume that the other double bond can go on this oxygen. Why not the top oxygen? Because that already has the 2 bonds that it requires, and I don't want to add a third bond, because if I did that, then it's going to not bond appropriately. So that is most likely the way that the drawing is going to work. All right, final part of this question, letter F. It says a student prepares a solution containing equal molar amounts of the HC2H3O2 and the NaC2H3O2. The pH of the solution is measured to be 4.7. The student adds 2 drops of nitric acid, 3 molar nitric acid, and stirs the sample, observing that the pH remains at 4.7. Write a balanced net equation for the reaction between the HNO3 and the chemical species in the sample that is responsible for the pH remaining at 4.7. First off, the very fact that we have equal amounts of this and that, you should be thinking buffer solution, right? I mean, this is what's happening. You have this weak acid, acetic acid, and then it's going to break apart into H plus and the acetate ion. So if you have equal amounts, you're going to have a certain amount here and a certain amount of the ion over there on the product side. So that is the definition of a buffer. Well, if I'm going to add nitric acid, again, you got to be smart about this. Nitric acid deals with H+. So if I wrote H+, if I look at that equation above, it's just the reverse. How do I know that? Because what would bond or react with a positive ion? A negative ion. So I would have to do the acetate ion first, and then it would create the weak acid on the right side, or the product side. So that is the equation, and that's all it's asking. So did you understand that it's actually just the opposite of the original equation that I drew above? So that is an overall review of some problems that go over thermodynamics, kinetics, and equilibrium problems for big ideas number 4, number 5, and number 6 for the AP